If you stand next to a modern main battle tank, your entire body vibrates from the deep, deafening rattle of a massive diesel engine. But when the American M1 Abrams rolls up, there is no rattle, just a high-pitched, terrifying hiss. Why did the US military decide to put a modified helicopter jet engine inside a 70-ton armored beast? It was a radical, highly controversial engineering choice that almost killed the entire Abrams project before it even started. While the rest of the world chose the reliable, fuel-efficient path of heavy diesel, America went all in on a thermodynamic wildcard. Today, we break down the mechanical genius and the logistical madness of the AGT-1500 gas turbine. Welcome to Weapons Science. I'm Ethan Walker. To understand why the US chose this path, we have to look back at the Cold War arms race, where speed, survival, and raw power outweighed every rule of conventional engineering. For nearly a century, diesel has been the undisputed king of armored warfare. From the legendary T-34 to the modern British Challenger, heavy compression ignition engines have powered the heavy metal of global militaries. The reasons are simple. Diesel fuel is extremely stable, highly energy dense, and far less likely to explode when hit by enemy fire compared to highly volatile gasoline. It was the safest choice for a steel coffin. Furthermore, diesel engines excel at producing massive low-end torque. When you are trying to move a 60-ton vehicle through deep, sticky mud or up steep, ruined hills, torque is your absolute best friend. Diesel engines are also incredibly thermal efficient. They convert a high percentage of their fuel's chemical energy into actual mechanical work, allowing tanks to operate for hundreds of miles without refueling. And finally, there is the simplicity of maintenance. Any mechanic who can fix a commercial semi-truck can, with a bit of training, keep a military-grade diesel engine running in the middle of a war zone. But by the late 1960s, the US military realized that traditional diesel engines were reaching their physical limits. To make tanks heavier and better protected, they needed a power source that was far more compact. Adding more armor meant adding more weight. To keep those heavier tanks mobile, you needed more horsepower. But a bigger diesel engine meant a bigger engine bay, which in turn required even more heavy armor to protect it. This vicious cycle of weight and size forced American engineers to look beyond the piston. They needed something with an unprecedented power-to-weight ratio. They needed to think like aerospace engineers. Enter Chrysler Defense. In the early 1970s, during the development of the XM1 prototype program, they made a high-stakes gamble that shocked the entire defense establishment. They proposed a gas turbine. The proposal was met with immediate, fierce skepticism. The U.S. Army had spent decades mastering diesel technology. Turbines were seen as delicate, complex machines meant for high-altitude jets, not dusty battlefields. Critics argued that a turbine would suck in massive amounts of dirt and sand, destroying its high-speed internal blades within minutes of entering a desert combat zone. It seemed like a recipe for instant mechanical failure, but Chrysler had an ace up their sleeve. They partnered with Lycoming, a legendary aviation engine manufacturer, to adapt the proven technology of helicopter turbines for the brutal realities of ground combat. They designed a massive multi-stage air filtration system that would wrap around the engine, ensuring that only pure, clean air could ever reach the sensitive, rapidly spinning turbine blades. This wasn't just about survival, it was about performance. The proposed AGT-1500 gas turbine promised 1,500 horsepower in a package that was half the weight of a comparable diesel engine. The Army decided to run a head-to-head competition. Chrysler's turbine-powered prototype went up against General Motors' traditional diesel-powered entry in a series of grueling endurance and speed tests. During the trials, the turbine-powered tank demonstrated mind-boggling acceleration. It didn't need to build up RPMs like a diesel. It delivered maximum torque almost instantly, leaping forward like a sports car. Even more surprising was its reliability. Despite the initial fears, the turbine engine had far fewer moving parts than a piston engine, meaning there were fewer components that could wear down and break. In 1976, the Secretary of the Army made the historic decision. Chrysler won the contract. The turbine was officially selected as the heart of America's next-generation main battle tank, the M1 Abrams. It was a monumental gamble. The United States was now the only nation in the world committed to deploying a turbine-powered main battle tank on a massive strategic scale. The pressure was immense. To understand why this gamble paid off, we have to look under the armor and examine the fascinating physics of how a gas turbine actually operates compared to a traditional internal combustion engine. A diesel engine relies on a reciprocating cycle. Pistons move up and down, converting linear motion into rotational energy through a crankshaft. This process involves constant stopping, starting, and massive friction. The AGT-1500 gas turbine, however, operates on a continuous flow cycle known as the Brayton cycle. Air is constantly drawn in, compressed, mixed with fuel, ignited, and exhausted in a smooth, uninterrupted stream. It starts at the compressor stage. The AGT-1500 uses a two-spool compressor system. A low-pressure compressor and a high-pressure compressor work together to squeeze the incoming air to massive pressures. Next is the recuperator. This is the secret weapon of the AGT-1500. It takes the hot exhaust gases from the rear of the engine and uses them to preheat the compressed air before it even enters the combustion chamber. By preheating the air, the engine requires far less fuel to reach its optimal combustion temperature. Without this recuperator, the Abrams fuel consumption would be twice as bad as it already is. Once the preheated high-pressure air enters the combustor, fuel is continuously injected and ignited. This creates a high-velocity superheated gas stream that rushes toward the turbine blades. This expansion of gas drives the turbine wheels. The first set of turbines powers the compressor stages to keep the cycle running. The second, independent set of turbines, the power turbine, drives the tank's transmission. Because the power turbine is not mechanically locked to the compressor, it acts like a built-in torque converter. This allows the engine to deliver massive torque even when the tank is completely stationary. The entire engine spins at mind-boggling speeds. While a diesel engine redlines at around 3,000 RPM, the high-pressure spool of the AGT-1500 spins at over 43,000 RPM. To convert that insane rotational speed into usable power for the tracks, the engine is paired with an incredibly robust Allison transmission, which reduces the RPMs while multiplying the torque. The result is a propulsion system that is silky smooth. There is no vibration, no clutch hesitation, and no sudden gear shocks. It is a level of automotive refinement unheard of in armored vehicles. But engineering is always a series of trade-offs. What did the US military gain on the battlefield by choosing this complex, high-speed jet engine over a traditional battle-tested diesel? The first major tactical advantage is acoustic stealth. In the military world, the M1 Abrams is famously known as Whispering Death, and that nickname is entirely earned because turbine engines do not have heavy pistons slamming up and down inside metal cylinders. They do not produce the low-frequency rumble that travels for miles through the ground and air. Most of the noise from a turbine is high-pitched, which is highly directional and dissipates rapidly over short distances. In combat, an enemy often won't hear an Abrams coming until it is right on top of them. The second advantage is instant battlefield mobility. The AGT-1500 allows the 70-ton Abrams to accelerate from 0 to 20 miles per hour in just over 6 seconds. That is faster than many standard cars. In a tank duel, mobility is armor. Being able to quickly dart out of cover, fire around, and retreat before the enemy can target you is a massive life-saving advantage. Then there is cold weather reliability. Diesel engines are notorious for struggling to start in sub-zero temperatures. The diesel fuel can gel up, and the heavy engine blocks require extensive preheating. The AGT-1500 gas turbine, however, doesn't care about the cold. It can start reliably in temperatures as low as -40 degrees Fahrenheit within a matter of seconds without any preheating cycle. This makes the Abrams incredibly responsive in Arctic or deep winter scenarios, where a diesel-powered force might find themselves frozen in place and vulnerable to a sudden coordinated surprise attack. Additionally, the turbine engine produces an immense amount of waste heat. While this might seem like a drawback, it is actually used to run a highly effective crew heating system, keeping the soldiers combat ready. The engine is also remarkably modular. If a turbine is damaged in combat, the entire power pack can be unbolted, lifted out, and replaced with a fresh unit in less than an hour by a skilled maintenance crew. Compare that to a traditional diesel tank, where replacing or repairing internal components can take days of complex teardowns, keeping the tank out of action when it is needed most. But of all the tactical advantages of the AGT-1500, there is one feature that sounds like pure science fiction: its ability to run on almost any liquid fuel you can find on the planet. Most engines are highly picky. Put gasoline in a diesel engine and you will destroy it within miles. Put diesel in a high-performance gasoline engine and it won't even start. The AGT-1500 gas turbine, however, is a true omnivore. Because it relies on continuous external combustion rather than timed internal explosions, it simply needs a fuel that can burn. The standard fuel for the US military is JP-8, a kerosene-based jet fuel. But if the supply chain breaks down, the Abrams can easily run on standard commercial diesel, high-octane gasoline, or marine fuel. In a desperate combat scenario, the fuel flexibility of the Abrams becomes a life-saving asset. If a crew is cut off from their logistics tail, they can siphon fuel from abandoned civilian gas stations, airports, or ships. The thermodynamics of the turbine are so forgiving that the engine could theoretically run on high-proof alcohol or even cheap perfume if those were the only combustible liquids available. This incredible adaptability is a massive strategic advantage. It means the US military doesn't have to ship specialized fuel across the globe. They can adapt to whatever energy resources are locally available. But this multi-fuel capability isn't just a parlor trick. It is a fundamental design requirement for a global expeditionary force that must be prepared to fight in any theater at any time under any conditions. However, this incredible flexibility and performance come with a catch. A catch so massive that it has defined the entire tactical doctrine of the US Army's armored divisions for over 40 years. That catch is fuel consumption. The AGT-1500 is not just thirsty, it is an absolute uncontrollable fuel-guzzling monster. It eats fuel at a rate that would bankrupt a commercial trucking company in days. To put it in perspective, a standard diesel tank might get around 5 to 8 miles per gallon. The M1 Abrams, on the other hand, does not measure fuel in miles per gallon. It measures fuel in gallons per mile. On average, the Abrams burns through more than 1.6 gallons of fuel for every single mile it travels, and that is under ideal road conditions. In rough terrain, that number skyrockets. This extreme thirst creates what military planners call the logistical nightmare. To keep a single division of Abrams tanks moving, you need an army of fuel trucks following right behind them. The biggest issue is idle consumption. Unlike a diesel engine, which can idle efficiently for hours using minimal fuel, a gas turbine must maintain a high compressor speed just to keep running. Even when the tank is completely stationary doing absolutely nothing, the AGT-1500 burns through roughly 10 gallons of fuel every single hour. In a long defensive hold, this is a massive waste of precious resources. To combat this, modern versions of the Abrams are equipped with an auxiliary power unit, a small, separate generator that runs the electronics when the main turbine is shut down. But the auxiliary power unit is only a partial fix. The broader logistical footprint of an armored division remains staggering. For every tank on the front line, there are multiple support vehicles dedicated solely to its survival. This logistical tail is the main reason why many US allies refuse to buy the Abrams. They simply do not have the massive, highly advanced supply chain infrastructure required to keep the turbine fed. For a nation with a defensive military doctrine, a fuel-efficient diesel tank, like the Leopard 2, makes far more sense. It can operate independently for longer periods without constant logistical handholding. But the United States military is not a defensive force. It is built for rapid, overwhelming global power projection, and in that specific role, the speed and power of the turbine outweigh the logistical cost. The US military has built the most sophisticated, capable logistics network in human history. They have accepted the fuel penalty of the Abrams because they have the unique ability to deliver fuel anywhere on Earth. This is a classic example of designing a weapon system around your strategic strengths. If you have unlimited fuel and unmatched logistics, you can afford to build the fastest, most powerful tank in the world. But as we move deeper into the 21st century, the rules of warfare are changing once again. Fuel efficiency is no longer just a logistical convenience, it is becoming a critical tactical survival factor. With the rise of long-range precision missiles and suicide drones, supply convoys are more vulnerable than ever before. A tank that requires constant fuel deliveries is a liability in a contested environment. This new reality has forced American military engineers to ask a difficult, once unthinkable question. Is it finally time to retire the legendary AGT-1500 gas turbine and return to diesel? The answer lies in the next-generation prototype, the Abrams DEX. Unveiled recently by General Dynamics, this experimental vehicle represents the most radical redesign of the Abrams platform in decades. And the biggest change is under the hood. The AGT-1500 gas turbine is gone. In its place sits a revolutionary hybrid diesel power pack, combining a high-efficiency diesel engine with advanced electric motors. This hybrid system promises to deliver the same 1,500 horsepower as the old turbine, but with a staggering 50% reduction in fuel consumption. It is a massive leap forward in efficiency. Even more impressive is the silent watch capability. The AbramsX can operate its electronics and even move at low speeds using pure electric power, making it completely silent and thermally invisible to enemy sensors. This hybrid approach combines the best of both worlds, the extreme torque and silent operation of electric power with the range, reliability, and fuel efficiency of a modern diesel engine. The era of the pure gas turbine tank may be drawing to a close, but the AGT-1500 will go down in history as one of the most daring, successful engineering gambles ever made in the history of armored warfare. It was an engine that defined an era of American military dominance, proving that sometimes the most insane engineering choices are the ones that actually change the world. What do you think? Should the US military stick with the turbine, or is it time to embrace the hybrid diesel future? Let us know in the comments below. Don't forget to subscribe to Weapon Science. I'm Ethan Walker, and I'll see you next time.